This video is going to show you the solutions to the problems in the speed camera tutorial set. 1. In this problem, we're told that a person is sitting in a kayak out at sea. They rise and fall as the waves pass them. They notice that the period of the waves is 1.2 seconds. And here's the waves going past. Here's the person in the kayak going up and down. And that the wavelength is equal to 6.2 meters. And part A of the question asks, what is the frequency of the wave? Well, to calculate the frequency is the inverse of the period. So that's 1 divided by the period. So 1 divided by 1.2 seconds gives us 0.83333, and the units for frequency are hertz, or you can put it as inverse seconds if you want. Now, this is just to two significant figures, so we should give our answer to two significant figures, so 0.83 hertz. Now, part B says, what is the speed of the wave? In order to answer this one, we're going to need to use our equation V is equal to F lambda, where F is the frequency and lambda is the wavelength. So we now got the frequency, so we've got 0.83333 times the wavelength, which is the 6.2 meters, and this gives us a speed of 5.167 meters per second, but we should just give our answer to two significant figures, so this is equal to 5.2 meters per second. Problem 2. So we're told that a radio tower sends out a radio signal with a wavelength of 2 meters. So here's the radio tower, and it's sending out signals, and the wavelength is equal to 2 meters, 2.0 meters, so two significant figures. And part A says, what is the speed of radio waves? Well, in order to answer this one, we need to realize that radio waves are just electromagnetic radiation, and all electromagnetic radiation travels with the same speed. So the speed is equal to the speed of light, which is 3.00 times 10 to the 8 meters per second. This is going through air. Air is very close to a vacuum, so light travels at almost the same speed in air as a vacuum. So this is the correct answer. Part B says, how long does it take for the wave to travel 2 kilometers? So we know that time is equal to the distance over the speed. So this is equal to 2 kilometers, which is 2,000 meters, over the speed, which is 3.00 times 10 to the 8. And so this gives us, when we solve it on the calculator, 6.667 times 10 to the minus 6 seconds, which to two significant figures is 6.7 times 10 to the minus 6 seconds. We would expect a very small number here because light travels very, very quickly. So it doesn't take light very long to travel a short distance like 2 kilometers. Part C asks, what is the frequency of the wave? Well, to answer this one, we'll need to use our wave speed equation, V is equal to F lambda. We can rearrange this one to get the frequency. The frequency is equal to the speed over the wave over the wavelength. The speed is 3.00 times 10 to the 8, and the wavelength is 2 meters. And so this gives us 1.5 times 10 to the 8 meters per second, to two significant figures. Part D asks us, what is the period of the wave? Well, the period is equal to 1 over the frequency, the inverse of the frequency. And so the period is 1 over 1.5 times 10 to the 8. And so the period is 1 over 1.5 times 10 to the 8. Whoops, we've got the wrong units here. This should be the units for frequency because it's the frequency we've found. So this should be inverse seconds or hertz, not meters per second. So this is 1 divided by 1.5 times 10 to the 8 hertz. And solving that on the calculator, we get 6.7 times 10 to the minus 9 seconds is the period.
Okay, so we're up to problem 3. This is one where we need to do diagrams. So in case 1, we've got a flat piece of rope like that, and we're told that 1 meter is around about this long, and that the wavelength is 1 meter and the amplitude's 10 centimeters, and case 1 is a transverse wave. So for a transverse wave, the particles in the rope, the little increments of rope, move in a direction perpendicular to the wave. So this is one wavelength there, and so the rope is going to look like that. Not perfectly drawn, but quickly sketched, and the amplitude's 10 centimeters. So that there is 10 centimeters, and the distance here is the 1 meter, which was what it was marked on that diagram. And then we're asked to draw 2 diagrams. So the second one's meant to be a quarter of a period later. So let's just sketch the flat rope there. And now if we assume that the velocity of the wave is going in this direction, then a quarter of a period later, this point on the wave here is going to have moved to here. So let's just draw that in a different color. This point will have moved to there. And so when we draw this wave, we can start here. That is 1 meter. This is 10 centimeters. Okay, so now in case 2, we've got a spring and we're sending a longitudinal wave down it. So we've represented the little loops in springs by the little lines here. And initially they're all at their equilibrium positions. These are all meant to be evenly spaced, but because I'm drawing it by hand, they're not perfect. And here's 1 meter. Now, as we send the longitudinal wave down the spring, we're going to have rarefactions and compressions. So let's initially start with a compression at this end. So at this end, we draw the bits close together, and then they spread out, and then they're close together. So 1 wavelength, we have the compression, the rarefaction, and back to the compression. And we should have the same number of lines in 1 meter here as we have in 1 meter up there. I'm not sure if I do exactly because I'm just sketching this roughly. And then through our spring, we go from compression to a rarefaction, compression, rarefaction, compression, etc. Okay, now if we consider what happens a quarter of a period later, this compression has moved on quarter of a wavelength. So it's moved on 25 centimeters. And this rarefaction in the middle here has also moved on 25 centimeters as well. Okay, so we have our compression around about here. So that's where they're closest together. And then our rarefaction is around about here. So rarefaction is spaced out. And this compression's moved on to here. So just roughly sketching it, it'll look a bit like that.
Problem 4. In this problem, we're told that seismologists can locate the position of the epicenter of an earthquake by comparing the arrival time between 2 different types of waves at 3 locations. These waves are primary waves, or P waves, with a speed of 4,800 meters per second, and secondary waves, S waves, with a speed of 2,900 meters per second. And part A, we're told that P waves are longitudinal waves, and we're asked to use a diagram to explain what a longitudinal wave is. Okay, so let's draw what happens to particles as a longitudinal wave passes. So we get compressions and what's called rarefactions. And the distance between two compressions is the wavelength of the wave. And what makes this a longitudinal wave is that the particles making up the medium are displaced in a direction parallel to the movement of the wave. So the velocity of the wave is in this direction, and these particles move backwards and forwards in the same direction parallel to the velocity of the wave. Part B asks us, S waves are transverse waves. Draw a diagram showing what a transverse wave is. Okay, so a transverse wave looks like this. The particles move up and down, and the velocity of the wave is in this direction. This is one wavelength here. So the particles making up the medium through which a transverse wave travels move perpendicular to the direction the wave travels in. And now part C. We're told at one base station the P wave is detected 3.5 seconds before the S wave. So we know that TP is less than TS as the P wave is detected first, and we can write an equation with this information in it. The arrival time of the S wave minus the arrival time of the P wave is equal to 3.5 seconds. Let's call that one equation 1. And we're asked, what is the distance of the base station from the epicenter? We know that distance is equal to speed times time. So we've got that the distance is equal to the velocity of the P waves times the time it takes the P waves to travel to the base station from the epicenter. And we also have that the distance is equal to the velocity of the S waves times the time it takes the S waves to travel to the epicenter. So what we can do now is equate these two together, because this is the same distance. This is the distance from the epicenter to the base station. So this tells us that VP TP is equal to VS TS. And so TP is equal to VS TS on VP. Now let's call this equation 2. And what we can do is substitute equation 2 into equation 1. So sub 2 into 1. So this tells us that TS minus, instead of writing TP, we'll put VS TS on VP is equal to 3.5. So rearranging this, we can pull TS out as a common factor, and we've got 1 minus VS on VP is equal to 3.5. Okay, we need to make some more room. We'll continue up here. So we've got TS is equal to 3.5 divided by this, which is 1. Now VS, the velocity of the S waves, we're told is 2,900 over the velocity of the P waves, which is 48,000. And so this is equal to 8.84 seconds. The question has asked us to find the distance, so what we can do is now substitute back into this equation here to get the distance. So the distance is equal to 8.84 times the velocity Vs, which is 2,900. So this is equal to 25,642 meters, which is equal to 26 kilometers to 2 sig fig, which is scarily close really. So if you wanted to check this, what you could do is work out what TP was and just check that that gives you the same answer as well. Now to do part D, let's just clear some more space. So part D asks us, can you think of a reason 3 base stations are required to pinpoint the epicenter? If we have one base station, then we know that the earthquake epicenter is a certain distance away. So it can be anywhere here. We could work out what this distance here was. This is base station 1. And so we know that it's somewhere on a circle. If we have 2 base stations, so here's base station 2, and this has got some other D, so we know that the earthquake is some fixed distance from this base station, which tells us that the epicenter could be here or here. We don't know. There's 2 options. Both these options satisfy the requirements. There's actually a few more than 2 options if we consider that the epicenter could actually not be on the surface of the Earth. It may be below the surface of the Earth, in which case, rather than just being circles, these are spheres. And so wherever these intersect, that's an option for where the earthquake came from. But if we have a 3rd base station and we measure the distance from this base station and we know it's this distance here, let's call this D3, then we know at which point the epicenter is, because there's only one point where all of the 3 spheres or circles intersect each other. Problem 5. So in this problem we have a low density medium with a pulse travelling along it, and it gets to a higher density medium here, and we're asked what happens once the wave gets here. Well, a couple of things happen. First of all, some is reflected and some is transmitted. The transmitted pulse, as this is a more dense medium, is going to have a smaller wavelength. So it'll be a bit compressed up like this. So it's going to travel slower through this medium. When it gets reflected off this end here, because it's being reflected off a more dense medium, it's like being reflected off a fixed end. So it does undergo a phase change and it actually comes back underneath. So this wavelength should be the same as this one. And then in the second figure, we have a pulse going through a more dense medium, and then getting to a less dense medium, and we're asked the same thing. Some of it is transmitted through this less dense medium. It has a longer wavelength than the less dense medium and travels faster. Longer wavelength, and some of it is reflected. When it's reflected off a less dense medium, and so it doesn't undergo a phase change. So it's reflected back on the same side of the string. So these two should have the same wavelength. This wave is travelling in this direction and this one's travelling in this direction. So that's everything we can say about that question.
Problem 6. So in this question we're asked to define what's meant by simple harmonic motion. So a good definition is that in simple harmonic motion, the force on an object is, and then there's two criteria. It needs to be directed towards the equilibrium position. And secondly, it needs to be proportional to the distance from equilibrium. Okay, and then it asks us, is a bouncing ball an example of simple harmonic motion? Why or why not? Okay, so a bouncing ball is not an example of simple harmonic motion. So a bouncing and the reason is that the force is constant and always directed downwards. And then we're asked about a mass on a spring. So a mass is an example of simple harmonic motion when the spring obeys Hooke's law, which is F is equal to minus kx, and that's because as this equation gives a force back towards the equilibrium position, as we've got the negative x there, so the force is directed in the opposite direction to the displacement, and it's proportional and is proportional to the distance from equilibrium. So that's x. So that's because there's an x in this equation here. So the force is proportional to the displacement. X stands there for the displacement from equilibrium. Okay, so this is problem 7. And in this problem, we're told that a 1 kilogram mass undergoes on the spring with a spring constant K of 2 newtons per meter, undergoes simple harmonic motion with an amplitude of 5 centimeters and a period of 10 seconds. And at t equals 0, it's at equilibrium position, so it starts at its equilibrium position. And in part A, we're asked to sketch a displacement time graph. So let's put displacement on the y-axis, so that stands for displacement from equilibrium, and this is time along here. And we're told it starts at its equilibrium position. So we can draw it undergoing its oscillations like this, and we know one period is 10 seconds. So that's at 10 seconds. We can put this at seconds, we can put this at centimeters. So here it's at 5 centimeters, and down here it's at minus 5.0. So at this point here, we've got a short spring, and down here we've got the spring is extended. So the distance between here and here is 2a, which is 10 centimeters. And then halfway between, well, here's halfway between again, the spring returns to its equilibrium position. And here it's at equilibrium as well, which is halfway between these two. So we've just sketched the little what's going on with the mass on the spring here. So hopefully that'll help us with the future parts. Okay, so let's mark on some more times along here. Okay, and then in part B of the question, we're asked to sketch a graph showing the velocity versus time graph for the motion. Okay, so we're going to want to put velocity up here, and we can put the time here. Now, we can actually work out what the velocity is going to be, because we know that for simple harmonic motion, x is equal to a cos omega t plus phi, and so the velocity is equal to minus a omega sine omega t plus phi. So from this we can see that the maximum value that the velocity can have is going to be equal to minus a omega. Well, we don't need the minus for the maximum value, it'll be a omega, and omega is equal to the square root of k on m, which in this case is equal to the square root of 2 on 1, and so this is equal to root 2, which is equal to 1.41, and that's radians per second. And so the maximum velocity is going to be a, which is 0.05 meters times 1.41, and so that is going to be equal to 0.071 meters per second. Okay, so we know what the maximum speed is. Now, for simple harmonic motion, the maximum speed occurs when it's going through its equilibrium position. So that's right at the start here. And at the start, it's moving upwards. So we'll take that as positive. So it starts here at 0.71. And now when it reaches that maximum height, that's when it's changing direction. So if we kind of draw that down here, that's when it's going to be at zero velocity, because it's changing direction, so it's not actually moving in either direction. And then here, when it's going through that equilibrium position again, it's going to have its maximum velocity, but in this case it's moving downwards, so that's a negative maximum velocity, so that's minus 0.71, and this is the velocity in meters per second. And so you can see that it's going to look like this. Now that's 0, this is 5, this is at 2.5, this 10, once again that's maximum and positive, so that's going to go up like that, so that's 10 seconds, and so at 20 seconds it's upwards and positive again. And so it's going to look like this. That goes through 0 at 7.5 seconds. So that's what the velocity versus time graph looks like. And then in part C, we're asked for an acceleration versus time graph. And the acceleration is the derivative of the velocity. And we know that it's given by minus a omega squared cos omega t plus phi. So that equals, we know that a cos omega t plus phi, that's x. So this is equal to minus omega squared x. So this is just going to be a constant and negative of this one here. And so the maximum value this can have is a omega squared, which omega squared is the square root of 2 squared, so that's 2 times a, which is 0.05 meters, because it was 5 centimeters. So this is going to be equal to 0.10 meters per second per second. So if we put a in meters per second here, and t here, and we know that when this has a maximum positive value, because of this negative here, the acceleration is going to have a maximum negative value. So we'll start with no acceleration, and then we'll go down to minus 0.10 meters per second. And we'll have a graph like this. So it goes up, and then at 10 seconds it's at 0 again. And sorry, that's a bit messy. These should all have the same amplitude. They're all going between 0.10 meters per second and minus 0.10 meters per second. And so that's at 20 seconds, it's back to 0, and then at 30 seconds, it's back to 0. So a bit of a messy sketch, but you get the idea about how to sketch these graphs, hopefully. Okay, so this is problem 8. So with this problem, we said that an object moves with simple harmonic motion and has a maximum acceleration. So the maximum acceleration is equal to 10.0 meters per second, and the amplitude of the motion is equal to 0.20 meters, and we have to come up with an expression for the displacement, the velocity, and the acceleration. And we're told that it starts from its maximum displacement above its equilibrium point. So we know that at t equals 0, x is equal to 0.20 meters, the amplitude, which is the maximum displacement. Okay, so we know for simple harmonic motion, x is equal to a cos omega t plus phi. Now at t equals 0, it's got its maximum displacement. So we've got that we've got a cos omega t, where t is 0, so this is 0 plus phi, and this has to have its maximum value. So cos has its maximum value when the angle in here is 0, because cos of 0 is equal to 1. So what we need is for this thing in here, 0 plus phi, to be equal to 0. And so that tells us that phi is equal to 0. So we've got x is equal to a, which we're told is 0.20. And we've just worked out that phi is 0. So this is cos omega t. So that's the expression for x, but we don't know omega yet. So we're going to need to try and work out what that is. So to work out what that is, let's write down our expression for the velocity. So the velocity is the derivative of this, or if you don't know how to do derivatives, remember that it is equal to negative this thing, the amplitude, times omega sine omega t, and then the acceleration is the derivative of this, which ends up being minus 0.20 omega squared cos omega t. And there is something that we know about this acceleration. We were told that the maximum acceleration is 10 meters per second. So the maximum value this can be is when cos omega t is 1. And so we've got a max is equal to 0.20 omega squared, and we know that that is equal to 10. And so this tells us that omega squared is equal to, just rearranging this, we've got 10 divided by 0.20, which is equal to 50. So omega squared is 50. Okay, so what we can work out omega now. So omega is equal to the square root of 50. And if we work that out on the calculator, we end up with 70.07, which is equal to 7.1 to 2 significant figures, as the amplitude was only given to 2 significant figures. Okay, so now we can substitute everything into these expressions here to give our final expressions. So x is equal to 0.20 cos omega, which is 7.1 t. V is equal to minus 0.20 times omega, which is 7.1. So we do that on the calculator and we get minus 1.4 cos omega, sorry, this is sine, not cos. We have the sine written here. So that's sine omega t, which is 7.1 t. And A is equal to minus 0.20 times omega squared. So remember, omega squared was 50. So 0.2 times 50, that's 10. So this is minus 10 cos omega t, which is 7.1 t. And we should just check the maximum value of this one is when cos of this is minus 1, and that gives us 10, which is what we were given in the question. So it seems consistent. It's always a good idea to just check our answers. Okay, so those are the three expressions that we were asked for in this question. Actually, we should just include units in this as well. 0.20, that's from the same as the amplitude here, that's in meters. 1.4, that's in meters per second, it's a velocity, and then the acceleration, that's got the same units as this acceleration, meters per second per second. Okay, this is problem 9. This one's quite hard. So we've got at t equals 0, a mass has velocity 2.0 meters per second upwards. So let's write the initial velocity. So we'll show its initial with a little subscript 0 here. So the initial velocity is 2.0 meters per second. So we're going to take upwards as positive. And its displacement is 0.10 meters below its equilibrium position. Okay, so the displacement is x, and this is the initial displacement, so we'll put a little subscript 0, and this is below, so this is minus 0.10 meters. The mass is undergoing simple harmonic motion. Exactly 2 seconds later, it returns to the same position with the same velocity. Okay, so because it's at the same position with the same velocity, that tells us that one period has passed. So the period is equal to 2.0 seconds. And then in part A, we're asked to come up with an expression for the amplitude. Okay, so we can write for simple harmonic motion, x is equal to a cos omega t plus phi. And we're going to want to find out as many of these things as we can. So omega is fairly easy. Omega is equal to 2 pi f. So that's equal to 2 pi over the period, because the period is the inverse of the frequency. So that's 2 pi over 2, and so that is equal to pi. And so we have x is equal to a cos pi t plus phi. Okay, now we want to work out what the amplitude is. That's part A, to work out this amplitude. And to do that, we'll probably need to work out what this phi is. So let's substitute in what we know. We know that at t equals 0, x is equal to x0. So we've got minus 0.10 is equal to a cos pi times 0 plus phi. So we can write this as a cos phi. Okay, so that's one thing we know. We also know a bit about the velocity. So let's write down an expression for the velocity. Using this, we know what omega is. So the velocity is equal to minus a omega sine omega t plus phi. And so this is equal to minus a pi sine omega t plus phi. And then we know at t equals 0, v is equal to v0. So we've got v0 is 2.0, and then this is equal to minus a pi sine, and then omega, that's pi times 0 plus phi, and so that equals minus a pi sine phi. Okay, so let's call this equation for x here, let's call that, we'll just move this here. Let's call that equation 1, and let's call this one equation 2. Now, we can do a couple of trigonometric tricks here to work out what phi is and also what a is. Let's start with phi. What we'll be using is the relationship that sine phi on cos phi is equal to tan phi. Okay, so using this, we can put equation 2 over equation 1. Okay, so equation 2, we've got the left-hand side is 2, and here we've got that's over minus 1.0. And so that is equal to minus 20. And that is equal to, on the right-hand side of this, we've got minus a pi sine phi. And here on the right-hand side, we've got a cos phi. And so these a's cancel out. and the negatives also cancel out. So we can write this as 20 over pi is equal to sine phi on cos phi, and we know that this is equal to tan phi. So then using the calculator, we can say phi is equal to the inverse tan of 20 over pi. Okay, so we should solve this in radians as omega t, that's in radians. So putting this into the calculator, we end up with 1.41 radians. But then this question really is quite tricky. There's another trigonometric thing that we have to remember here, which is that the different functions are positive in different quadrants. So we have all stations to central. So tan is positive in the first quadrant, which is what this one's given us. This, when we put it into the calculator, it generally, if we have a positive number here, the calculator will give us the answer in the first quadrant. But the answer doesn't have to be in the first quadrant. So because tan's positive, it can either be in the first quadrant, where we've got the 1.41 radians there, or it could be in the third quadrant, and to get the angle in the third quadrant, we'll have 1.41 measured there, but the angle itself will be all around there. So this is pi radians, and then an additional 1.41 radians. So it's this, or it's pi plus 1.41, and pi plus 1.41 is equal to 4.55 radians. So later we'll work out which one of these two it is, but now at least we're down to two options. Okay, so we've got phi now, but the question asked us to actually find the amplitude. So to get the amplitude, we're going to make use of another trigonometric relationship, which is that cos squared theta plus sine squared theta is equal to 1. So to make use of this, we can do 1 squared, and now we would like 2 to be in a similar format to this. So let's just rearrange it and get 2 dash. So we have a sine phi is equal to minus 2 over pi. So, and let's call this 2 dash. Okay, so 1 squared plus 2 dash squared gives us 1 squared, that's a squared cos squared phi, plus 2 dash squared, which is a squared sine squared phi, is equal to minus 0.10 squared plus minus 2.0 on pi squared. Solving this part on the calculator, we end up with 0.415, and looking at this part, we can take a out as a common factor, so a squared out, times cos squared phi plus sine squared phi. But cos squared phi plus sine squared phi is the same as cos squared theta plus sine squared theta, and that's always equal to 1. So this is 1, so we've got a squared is equal to 0.415, and so that tells us that a is equal to 0.64 meters. Okay, so we've solved it for a, but it's a good idea now just to check, and going on we're going to need to know which of these is the right option. Okay, so let's have a look back now to check. Let's check this part here. So we have x is equal to a, which is 0.64, and then that's times cos of pi t plus, well, is it 1.41 or 4.55? If we put 1.41, then we end up with 0.64 times cos. Now we're looking at time 0 because that's the information we have. So we've got cos of 1.41. Solving this, we end up with 0.10. Now that's a problem because it should have been minus 0.10. So that tells us that probably this 1.41 is incorrect and we should use 4.55. So let's check 4.55. So in that case, we've got x is equal to 0.64 cos, and here we'll use t equals 0 again, but we'll put in 4.55. And then when we solve this on the calculator, we end up with minus 0.10. So that's good. Okay, and then just to double check, let's look at V. So V is equal to minus a omega. That's from this line up here. So we've got minus 0.64 times omega, which is pi, times sine. Now, omega t, we're looking at t equals 0 here, and we've said phi is 4.55. And solving this one on the calculator, we end up with 2.0, and 2.0 is what we were told for the velocity. So we're also happy about that. So we've now worked out that phi is equal to 4.55. Now, that'll be important for the next part, because in the last part of this question, we're asked to come up with an expression for the acceleration. So we know that the acceleration is equal to minus a omega squared cos omega t plus phi. And now we can just substitute in our values for here. So we've got minus 0.64 times omega squared, so that's pi squared, cos pi t plus 4.55. And so that is equal to minus 6.3 times cos pi t plus 4.55. And so that's the answer to this one. So we should just give this phi to two significant figures for our final answer. So we can write this as 6.3 cos pi t plus 4.6, and then the units, this here is in meters per second per second. Okay, so this is problem 10. In this problem, we're told that a travelling wave described by the equation y of x and t is equal to 2.1 sine 3x plus 2.0t plus pi on 2 meters. And in part A, we're asked what's the amplitude. Okay, so the approach we'll need to take with this problem is to equate this to the general equation for a standing wave, for a travelling wave, y is equal to a sine kx minus omega t plus phi. And then we'll be able to work out what all these things are. So part A asks us to find the amplitude, which is the number out the front. So the amplitude is equal to 2.1 meters. Part B now asks us to find the speed. So let's write down what we know. We know k, which is the wave number, 2 pi over lambda, is equal to the thing in front of the x. So this is equal to 3. So this tells us that the wavelength is equal to, just rearranging this, we've got 2 pi over 3. And so that is equal to 2.09 meters. And we know that omega is equal to 2 pi f, and it's also equal to the thing in front of the t, so 2 in this case. So that tells us that the frequency is equal to 2 divided by 2 pi. So that's 1 divided by pi, or 0.318 hertz. And then we're asked to find the speed. V is equal to f lambda. Or if you didn't want to work out what the frequency and the wavelength is, you could remember that the speed is also given by omega over k. And so we'll use f lambda because we calculated these here. So that is equal to 0.318 times 2.09. And solving this, we end up with 0.67 meters per second as the speed. Part C then asks us in which direction is the wave travelling. Okay, so when a wave's traveling to the right in the positive direction, the numbers in front of the x and the t have opposite signs. In this case, they've got the same sign, and so this wave is traveling in the negative direction, so to the left. So this wave is going to the left as the numbers in front of x and t have the same signs. And then part D asks us, is this a transverse or longitudinal wave? Now in this case, we've got a y here and an x here. So y and x are perpendicular to each other. That's what we mean by that notation. So the particles are traveling perpendicularly to the direction the wave is traveling. So this is a transverse wave. And then part E asks us, what is the maximum speed of the medium as the wave passes? Okay, so now we need to work out the speed of the medium. So the speed of the medium is the derivative dy dt. So we will need to differentiate in this case. So when we differentiate a sine function, we get a minus cos function. So we've still got the a out the front, minus a, and then we've got the omega, which in this case is the 2, so times 2 times cos of 3x plus 2t plus pi on 2, and that'll be in meters per second. And so we know from up here that a is equal to 2.1, and we're asked for the maximum value. So the maximum value here will occur when this can be 1 or minus 1, and since we've got a negative there, we'll want it to be minus 1. So V max will just be a times 2, and a is 2.1, so 2.1 times 2, which is 4.2 meters per second, is the maximum speed that a piece of the string moves with. This is problem 11. So in this problem, we're told that a transverse wave has a wavelength of 2 meters. It has an amplitude of 0.50 meters. It's moving in the positive direction, and it's got a period of 4 seconds. And we can assume that at t equals 0, x equals 0, and y equals 0. At t equals 0 and x equals 0, we have y equals 0. So the first part, part A, asks us to write an equation to describe the wave. So in order to do this, we're going to need to make use of the equation for a traveling wave. Y is equal to a sine kx minus omega t plus phi. Okay, so in this case, we know the amplitude. K is the wave number, 2 pi on lambda. So that's 2 pi on 2 in this case, so that is equal to pi. Omega is equal to the angular frequency, 2 pi f, which is 2 pi on the period, because the period is the inverse of the frequency, and so that's 2 pi on 4, or pi on 2. Okay, so we've got, in our case, y is equal to 0.50 sine k, which is pi x, minus pi on 2t plus phi meters. Now what we're going to need to do is work out this phi, and in order to do that, we're going to need to use our starting conditions, which were that at t equals 0, x equals 0, then we have y equals 0. So we have 0 is equal to 0.50 sine pi times 0 minus pi on 2 times 0 plus phi. And so we've got 0 is equal to 0.50 sine of phi. Now for sine of 0, well, we know that sine of 0 is equal to 0. So this tells us that phi is equal to 0 in this case. So we have the equation for the wave is y is equal to 0.50 sine pi x minus pi on 2t meters. Okay, so that's our answer to A. Part B then asks us to draw a diagram showing the medium at t equals 0. Okay, so here's are medium. This is the length along the medium. This is the height. And we know that at x equals 0, y equals 0. So this is just a traveling wave with a wavelength of 2 meters. And so we can draw it like this. This is one wavelength to here, so we know that's 2 meters. This occurs at 1 meter. So this will occur at 3 meters. This will occur at 4 meters. The amplitude, that's the maximum height, is 0.50. We should put that this is in meters. This is in meters, and it goes down to minus 0.50. So that is our wave at t is equal to 0. We're then asked to draw the medium 1 second later. Okay, so let's do that in green. This wave is moving in this direction here, and we need t is equal to 1 second, which is 1/4 of a period. Period, spell it right. Okay, so in a period, the wave travels 1 wavelength. In a quarter of a period, the wave travels 1/4 of a wavelength. So this point moves on to here. 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 And so you can kind of see how, and this point moves on to here. This point's here. Not a very neat diagram in the first place, but it looks like that. And then we start down here. So that shows us our wave at t equals 1 second. And then we're asked at t equals 3 seconds. So let's do that in this orangey color, t equals 3 seconds. So from this white wave, it's then moved on 3/4 of a wavelength. And so this point here has moved on, that's 1/4, 2/4, 3/4. So that point is up there. This point, that's half, and then another quarter. And so this point has moved on to up here. This point here has moved on to here. And we'll start up here. And so our wave is going to look like this, and we'll end up back up there. So we've gone down and up, down and up, 2 periods again. Okay, and then part E says, describe how an element of the medium at x equals 3 meters moves as the wave passes. Use an equation and words. Okay, so for an equation, we can work out how it moves, the height it has. We just substitute into here. So we've got 0.50, and then we've got sine. And then pi x, in this case it's 3 times pi minus pi onto t. So that tells us how it moves as an equation. Now what's happening is, because it's following the sine wave, it's undergoing simple harmonic motion. So it is undergoing simple harmonic motion with an amplitude of 0.50 meters, and it's got the same period as the wave, so the period's still 4 seconds, and a period of 4 seconds. Okay, so that's answered that problem. Problem 12.
This problem says that you are cycling along the road at 30 kilometers per hour. So here's you cycling along. Your velocity is equal to 30 kilometers per hour, which is equal to 30 times 1,000 over 60 times 60, which is equal to 8.33 meters per second. When an ambulance comes up behind you with its sirens blazing, so here's the ambulance behind you, it has a speed of 90 kilometers per hour, which is 90 times 1,000 over 60 times 60, which is equal to 25 meters per second. Now you hear a frequency, f dash, of 800 hertz. And in part A, we're asked what frequency do the people inside the ambulance hear. So these people hear the frequency of the source, which is what we give the symbol f to. So our Doppler equation is f dash, the frequency observed by the observer, is equal to f, the frequency produced at the source, v plus or minus VO, so this is the velocity of the observer, and this is the velocity of, in this case, sound, because it's sound waves, and this is over V minus or plus Vs, and this is the velocity of the source. And we take the top sign if they're approaching and the bottom sign if they're receding. So in this case, we know what f dash is. F dash is the 800. So we've got 800 is equal to the frequency of the source, which is what we're trying to find. Now, in this case, the observer, you on the bicycle, are moving away from the ambulance. And so we'll need minus VO over, and now in this case, the ambulance, the source, is approaching you. So we've got V minus Vs. So let's substitute in. We've got 800 is equal to F, and the velocity of sound in air, we're told, is 343, minus VO, which is 8.33, over 343 plus 25. And so this is equal to F times 1.052. And so F is equal to 800 over 1.052, which is equal to 760 hertz. And now part B, so this is the frequency which is actually produced by that siren. Part B says once the ambulance has overtaken you, so now it's in front of you. Here's the ambulance over here, still got the same velocity. We're told to assume that we all keep moving at the same speed. What frequency do you hear now? So in this case, we'll have f dash. We're trying to work out the frequency you hear, which is equal to the frequency at the source. Now, in this case, you are now approaching the source. This is the source, this is you, the observer, and so we have V plus V observer over, and now in this case, the source is receding from the observer, and so we need to take the bottom sign, the positive sign. And so substituting in 760, 343 plus 8.33 over 343 plus 25. Solving this on the calculator, we end up with 725 hertz. And so we can give this to two significant figures as 720 or 730 hertz. Either of those would be fine.
Problem 13.
So in this problem, we're told that two submarines, sub A and sub B, approach each other in a training exercise. Sub A, so sub A is the source, it sends a sonar signal with a frequency of 1200 hertz to sub B. The sonar signal travels through water with a speed of 1500 meters per second. So sonar is sound, but it travels a lot faster through water than through air. One of the reasons is that water is more dense than air. If sub A is travelling northwards with a velocity of 8 meters per second, so V of the source is equal to 8.000, and velocity B is travelling southwards because they're travelling in opposite directions, so V of the observer is equal to 6.000 meters per second, then we're asked in part A, as they approach each other, what frequency does sub B detect? So we're going to need to use our Doppler equation. F dash, so the frequency detected by the observer, is equal to F, the frequency produced by the source, over V, the velocity of sound in the medium, which in this case will be 1500, plus or minus the velocity of the observer over v minus or plus the velocity of the source. Now in this case they're both approaching each other, so for both of them we use the top sign. So we've got f v plus vo over v minus vs. Okay, so now we can substitute into this equation. The frequency of the source is 1200, the velocity of sound in water is 1500, the velocity of the observer is 6 over 1500 minus the velocity of the source, which is 8, and then solving that on the calculator we get 1211 Hertz, and that's to 4 significant figures, as everything's given to 4 significant figures. Now in part B, we're told that after passing and narrowly missing each other, so here's sub A, it continues travelling this direction, and here's sub B, it continues to move in this direction, and we're asked, now that they've passed each other, what frequency does B detect? So in order to answer this, we're going to have to go up to this equation here again. Now in this case, they're both receding from each other, so we need to choose the bottom symbol. So we've got V minus VO over V plus VS, and now here's our observer, so this is equal to 1200 times 1500 minus the 6 over 1500 plus the 8, and solving that one on the calculator we get 1189 Hertz, and that's to 4 significant figures.
Problem 14.
This one's quite challenging. Bats chase down their prey by sending out ultrasonic sound signals and then listening to the echo. This gives them information about their distance from the prey and the speed of the prey is travelling at. If a bat travels at 5 meters per second, okay, so here's our bat. It's travelling with a speed of 5.0 meters per second. It emits a chirp with a frequency of 40 kilohertz, and then it detects the reflected chirp with a frequency of 40.4 kilohertz from the insect trying to escape by flying directly away from the bat. So here's our insect. It's travelling in this direction away from the bat. And so the signal from the bat comes in this direction, bounces off the insect and comes back. Now in part A of the question, we're asked to write down an expression for the frequency detected by the insect, which we're calling f dash. Okay, so we know from the Doppler equation f dash is equal to f v plus or minus velocity of the observer over v minus or plus the velocity of the source. Now in part A, the source is the bat and the insect is the observer. And so just substituting in here, we've got the frequency detected by the insect is the frequency transmitted by the bat over this V stands for the velocity of sound. And in this case, the observer, which is the insect, is receding from the bat. So because it's receding, we need to use the bottom sign. So we've got minus V for the insect over the velocity of sound. And now in this case, the source is approaching the bat. So we take the top sign, which is the negative. So V bat. And so that's the answer to part A. Now in part B, it says write an expression for the frequency detected by the bat, F double dash, when it's reflected off the insect. So what we need to do now is actually now consider the insect as the source, as it's providing the reflection, and the bat is now the observer, as it's detecting the signal. And so we have F double dash, which is the frequency detected by the bat, is the frequency emitted by the source, which is this F dash. Okay, and now in this case, we've got the velocity of sound, and the observer is the bat. The bat is moving towards the source, and so we take this top sign. So this is plus V of bat. And the source in this case is the insect, which is moving away from the bat. So we take the bottom sign, so plus v of source. And now what we should do is, instead of having this f dash here, which is the frequency of the reflected signal, we can substitute in for f dash from up here, because these two are the same thing. So this is equal to f times the velocity of sound minus the velocity of the insect over the velocity of sound minus the velocity of the bat times the velocity of the sound plus the velocity of the bat over the velocity of the sound plus the velocity of the source, which in this case was the insect. And so that is the formula. Now part C says use this expression to calculate the speed of the insect. So now we're going to need to substitute everything in. The only unknown in this formula is actually the speed of the insect. So let's substitute everything in. F double dash, that's the frequency detected by the bat. So that's 40.4 times 1,000 hertz. F, that's the frequency transmitted by the bat. Now the velocity of sound, that's 343 minus the velocity of the insect over 343 minus, now the velocity of the bat is 5. And we've got 343 plus 5 over 343 plus the velocity of the insect. Okay, now we can divide this side by this. The 1,000s cancel out. So 40.4 divided by 40 gives us 1.01. And we've got 343 plus 5, so that's 348, over 343 minus 5, which is 338, times the 343 minus the velocity of the insect, over 343 plus the velocity of the insect. Okay, so we can move these numbers over to this side, and we end up with 0.98097 is equal to 343 minus the velocity of the insect over 343 plus the velocity of the insect, and then multiply both sides through by the denominator, and when we do that we get 336.47 plus 0.98097 velocity of insect is equal to 343 minus the velocity of the insect. Move the two velocity of insect terms to the left side and the numbers to the right side. We have 1.98097 times the velocity of the insect is equal to 343 minus 336.47. And then we can just divide by 1.98097 to find the velocity of the insect. So this gives the velocity of the insect as 3.3 meters per second. And so D, does the bat catch the insect? Well, yes, it's going at 5 meters per second. The insect's going at 3.3 meters per second. So eventually the bat will catch up to the insect. So yes.
Problem 15.
So in this problem, an ant, a snail and a lizard have a race. They all head northwards with speeds. So here's our ant. The ant is equal to 6.56 millimeters per second, which is equal to 6.56 times 10 to the minus 3 meters per second. And then the snail goes with a slightly higher velocity of 0.13 meters per second, and the lizard is quite speedy with a velocity of 0.500 meters per second. And in part A, we're asked what is the velocity of the ant relative to the lizard. So the velocity of the ant relative to the lizard is equal to the velocity of the ant minus the velocity of the lizard. And so this is equal to 6.56 times 10 to the minus 3 minus the velocity of the lizard, which is 0.500. Solving this on the calculator, we get minus 0.493 meters per second. So this negative means south. So this is equal to 0.493 meters per second south. So if you were the lizard, it looks like the ant is moving away from you in the negative direction, the direction opposite to what you're actually travelling. Part B, we're asked what is the velocity of the lizard relative to the snail. So the velocity of the lizard relative to the snail, so that's equal to the velocity of the lizard minus the velocity of the snail. So now we imagine that we're the snail, and what would the lizard look like? It would look like the lizard was getting further and further away from us, but in front, so we'd expect this to be in the north direction. So the velocity of the lizard is 0.500, the velocity of the snail is 0.130, and so solving this on the calculator we get 0.370 meters per second, and as it's positive it's in the north direction. And then finally, part C. We're asked, what is the velocity of the ant relative to the snail? So the velocity of the ant relative to the snail. So while if we were the snail, it looks like the lizard is getting further and further ahead, it would look like the ant was getting further and further behind. So we'd expect this one to be in the south direction again. So we've got the velocity of the ant is 6.56 times 10 to the minus 3 minus 0.130, and solving that we get minus 0.123 meters per second, which we can say is 0.123 meters per second south.
Problem 16.
So in this problem, you stand on the bank. So let's draw a little diagram over here. Here's you standing on the bank and you watch your friend in a rowboat rowing across a river which is 25 meters wide. So this is 25 meters. And on still water, your friend can row at 5 meters per second. So, however, the river has a current that is flowing downstream at 2 meters per second. So we've got the river's current flowing down there at 2 meters per second, and your friend attempts to row directly across here, and that is at 5 meters per second. And part A asks us, what is the velocity of your friend relative to you? So in order to answer this question, we need to remember that velocity is a vector, so we need to work out the direction as well as the magnitude. So our friend, we see her rowing directly across the river with a speed of 5 meters per second, and then the current is affecting her speed downriver at 2 meters per second. So this angle in here is theta. So let's work out the magnitude first. We can use Pythagoras' theorem. These are perpendicular to each other. So we've got V is equal to the square root of 5 squared plus 2 squared. And so that's 25 plus 4, so the square root of 29, which is equal to 5.39 meters per second to two significant figures. We now need to work out this angle. So in order to work out the angle, we remember SOHCAHTOA. And what we've got is the opposite and the adjacent. So it'll be this TOA part that we'll use. So tan theta is equal to adjacent, which is 2 on 5. So this tells us that theta is equal to the inverse tan of 2 on 5. And solving that on the calculator, we end up with an angle of 21.8. And so the velocity is equal to 5.39 meters per second at an angle of 21.8 degrees to the line drawn directly across the river is one way to say it, or otherwise we could sketch this diagram here and say as shown in the diagram. Now for part B, we're asked how long does it take your friend to cross the river? And so we know that the velocity is equal to the distance over the time, and what we're going to be considering here is the direction directly across the river. And the reason for doing that is that we've got a length directly across the river of 25 meters. So let's rearrange this equation. We've got time is equal to distance over velocity, which is 25 over 5. So that's equal to 5 seconds. And so that's how long it takes her to cross the river. Part C, we've then got the question, how far downstream does your friend end up? So in this case, we're going to consider the direction parallel to the bank. So consider and in this case, we want to know the distance. So rearranging this equation here, we've got distance is equal to velocity times time. Now the velocity parallel to the bank is 2 meters per second, and the time is the 5. So this is equal to 10 meters downstream.
Problem 17.
So we're told that an ultrasound device uses a signal with a frequency of 7.00 megahertz. So that's 7.00 times 10 to the 6 hertz. This signal consists of sound waves with a velocity of 1,540 meters per second inside the human body. And part A, we're asked what is the wavelength of this signal inside the human body. So in order to do this, we just need to use our wave equation. V is equal to F lambda, which tells us that the wavelength is equal to the velocity of the frequency, which is 1,540 over 7.00 times 10 to the 6. And solving this one on the calculator, we end up with 2.20 times 10 to the minus 4 meters. So a small wavelength. Part B asks us if the signal takes 1.95 times 10 to the minus 4 seconds to return to the scanner after leaving the scanner and reflecting off part of the baby, how far is that part of the baby from the scanner? So we've got our scanner, it sends out the signal and receives the reflection, and we need to work out what this distance here is. So we know that distance is equal to speed times time. So we've got the speed is 1,540 meters per second. The time is 1.95 times 10 to the minus 4. So this gives us a distance of 0.3003 meters. Now that's the distance travelled by the signal, which is actually half the distance to the baby, as the signal has to travel to the baby and then back to the scanner. So this tells you that distance to baby will be half of this, which is 0.3003 on 2, which is equal to 0.150 meters to 3 significant figures. And that's the end of this tutorial set.